In the previous video, we developed these equations to calculate the confidence interval. Please review it if you need to. We have already used the z-score to find the area under the standard normal distribution to the left of a given z-score. In this case, we know the area to the left and need to find the z-score. And the area to the left of the negative z-score is 1/2 the value of alpha, making the area in the left tail 0.025. Because the z-score we're looking for is to the left of the mean, we will use the negative z-score table. We need to locate the area of 0.025 in the body of the table, and we find it here. We then combine the corresponding values in the row and the column to get the value of -1.96. That is, the z-score that has an area of 0.025 to its left is -1.96. We'll save the z-score we just looked up here. We now have all the values we need to calculate the value of -e. Minus z of alpha over 2 is the value we just retrieved from the table. Sigma of the population is 20, and the sample size is 4. This results in a value of -19.6. We'll save this result here. The z-score for the upper limit has an area of 0.025 to its right, which means the area to its left is 0.975. It is the value we will use to find the z-score. Since this value is to the right of the mean, we will use the positive z-score table. The area to the left of the z-score we're looking for is 0.975, using the corresponding row and column values to get a z-score of 1.96. This is the value of z that has an area of 0.975 to its left and 0.025 to its right. The positive z-score has the same magnitude but opposite sign. We'll save both z-score values here. Now that we have the positive z-score, we can calculate the positive e value. Using the same value for sigma and sample size as before, we get a result of 19.6, which is the same magnitude but opposite sign of the previous result. This will always be the case for e, the error, and is due to the symmetry of the normal distribution. Now that we have the value for e, we can calculate the lower limit, which is 80 minus 19.6, for a result of 60.40. The upper limit is 80 plus 19.6 for a result of 99.60. In summary, our confidence interval extends from 60.40 to 99.60, and we are 95% confident that the interval will contain the mean of the population. Another useful way to look at this is the probability of the population mean being between the values of 60.40 and 99.60 is 0.95, the value of the confidence interval. The probability of the population mean being outside these limits is the value of alpha, 0.5 or 5%. If we were to choose a confidence interval of 99%, that is, an interval where we have more confidence, it means that there is more area under the sampling distribution between the limits of the confidence interval. Because the limits are now further from the mean, the magnitude of the corresponding z-score is larger. Remember that the z-score is the number of sigmas a value is from the mean. The result is a larger interval, but the probability of the population mean being between these two values increases to 0.99 or 99%. If we increase the confidence interval a bit more to 99.5%, the magnitude of the z-score increases, the error increases a bit more to 28.07, but the resulting interval has a greater probability of containing the population mean. In summary, we can increase the amount of confidence we have in an interval with the trade-off that the interval increases in size. It follows then, if we were to reduce the confidence required, the error will decrease. As the error becomes smaller, the area under the sampling distribution becomes smaller, and the probability of the mean being between the interval's limits becomes smaller. Let's return to 95% confidence interval. By inspecting the equation for the error, we notice that the square root of the sample size is in the denominator, which implies that if we were to take larger samples, the error would decrease in size for the same confidence. As the sample size increases, the sampling distribution sigma decreases, which changes the shape of the sampling distribution. The error decreases, but the area between the interval limits remains the same. The result is a smaller error with the same confidence level, but with a larger sample size. Let's go back to a sample size of 4 and take another look at this equation. We use this equation to calculate the error for a sample size of 4, a population sigma of 20, and a confidence interval of 95%, and the confidence interval determined z of alpha over 2 to be plus or minus 1.96. So, if we solve this equation for n, we could then specify E and determine the necessary sample size. The first step is to divide through by plus or minus z of alpha over 2 to give us this result. Next, we invert both sides of the equation to get this result. Now we multiply through by sigma. The last step is to square both sides of the equation, which gives us this equation for n. We can drop the plus or minus sign for z of alpha over 2 because once squared it will be a positive number in either case. We'll save this equation here. Now we can specify an error and calculate the sample size required to achieve the specified error. Instead of 19.6, we will specify an error of 10 or less. We can now calculate the required sample size to achieve this error. We calculate it by using 10 for the value of E, 20 for the value of the population sigma, and recall for the confidence interval of 95%, we determined the z-score to be 1.96. We can now calculate the value for n, and it is 15.366. And because n must be an integer, we round this result up to the next integer, 16. Now let's increase the sample size to 16, and notice the error drops to 9.8. This is less than the 10 we specified, because the sample size of 16 is slightly more than the 15.366 we calculated. So, with this equation, we can determine the sample size required to meet a specified error.